Welcome to Lecture 13, in which we will discuss the Hermitian operator formalism for a measurement. This lecture is basically meant to help you better understand section 4.3. And for this lecture, I'm going to give several example problems that will be very similar to the problems that will appear at the end of the lecture. And hopefully these example problems will help you to better understand the examples in section 4.3 of your text. So example 1 is the following, and you might want to compare example 1 to example 4.3.2 in your textbook. But example 1 goes as follows. It says, circle each of the following that represents a valid Hermitian operator corresponding to measurement of a single cubit in the Hadamard basis. And you can see our choices here, A, B, C, and D. Okay, so let's see how we would do this. Well, first of all, let's remind ourselves of what the Hadamard basis means. Hadamard basis is that it is the plus cat and the minus cat, and remember that the plus cat is 1 over square root of 2 times the 0 cat plus the 1 cat, and the minus cat is 1 over square root of 2 times the 0 cat minus the 1 cat. So what we're saying here is that we're measuring a single cubit in the Hadamard basis, and of course we know in this case that the two resulting possibilities will be plus and minus, and the probabilities associated with those two different possibilities are determined by the particular cubit that's being measured. But we want to find a Hermitian operator that corresponds to this measurement. Now, the first thing we do, let's get just a little bit better idea of what we're talking about here. We're rewriting our space. V, in this case, is the space of all single cubit states, and that has a dimension of 2. And we're writing this as direct sum of two subspaces, S plus and S minus, where the basis for S plus is the single vector plus, and the basis for S minus is the single vector minus. Now, this means that if we use this idea of projectors, the projector that will project onto the S plus, I'll call it P plus. Well, that will simply be plus plus, and the projector that will project onto S minus will be minus minus. Now for the Hermitian operator, which we can maybe denote as O, We want it to contain both of these projectors, but we don't care in what proportion. So I'll say that it's equal to lambda 1 P1, or excuse me, lambda 1 P plus lambda 2 P minus. And again, the only requirements on lambda 1 and lambda 2 are the following. Since this is a Hermitian operator, lambda 1 and lambda 2 must both be real. And furthermore, we don't want them to be equal to each other. So lambda 1 is not equal to lambda 2. But those are the only restrictions that we have. So we have O is equal to lambda 1 plus lambda 2 minus. And let's see how this goes. Well, lambda 1 we bring down, and then each one of those, the plus ket and the plus bra, will both have a factor of 1 over the square root of 2 out in front. So, well, I guess I'll just take this one step at a time. So, okay, we'll have lambda 1, and then for the plus ket, we'll have 1 over square root of 2, 0 plus 1. And then for the plus bra, we have 1 over square root of 2, and then we have the 0 bra plus the 1 bra. And then for the second term, we will have lambda 2, and then for minus, we have 1 over square root of 2 times the 0 ket minus the 1 ket. And then for the minus bra here, we have 1 over square root of 2 times the 0 bra minus the 1 bra. And so now let's see what we can do with this. In this first term, we have 1 over square root of 2 here, 1 over square root of 2 here. So we get lambda 1 over 2 times 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. That's what we get from the first term. And then the second term will give us lambda 2 over 2. And again, you see we have 1 over square root of 2, 1 over square root of 2, so that's 1/2 times lambda 2. So that's how we get lambda 2 over 2. And then this time we will have 0, 0 minus 0, 1 minus 1, 0 plus 1, 1. And so now if we look at this carefully, we see that it can be written more compactly in the following way. We get 0, 0 times lambda 1 plus lambda 2 over 2 plus 0, 1 times lambda 1 minus lambda 2 over 2 plus 1, 0 times lambda 1 minus lambda 2 over 2. And finally, plus 1, 1 times lambda 1 plus lambda 2 over 2. Now, let's think about our matrix representation for each one of these operators. We have these operators 0, 0, 0, 1, 1, 0, and 1, 1. And if you review our last lecture, you will recall that the matrix form for 0, 0 is 1, 0, 0, 0 times, and then we have lambda 1 plus lambda 2 over 2. The matrix form for 0, 1 operator is 0, 1, 0, 0, and that's lambda 1 minus lambda 2 over 2. The matrix corresponding to the 1, 0 operator is 0, 0, 1, 0. Then we have lambda 1 minus lambda 2 over 2. And finally, the matrix corresponding to the 1, 1 operator is 0, 0, 0, 1. And then we have lambda 1 plus lambda 2 over 2. So when we add all of this together, our final answer is the following. Lambda 1 plus lambda 2 over 2, lambda 1 minus lambda 2 over 2, lambda 1 minus lambda 2 over 2, lambda 1 plus lambda 2 over 2. This is the form that the matrix must assume for this problem. Now let's go back up to our choices and see which ones are valid. Remember, what we're supposed to do is to circle each of the following that represents a valid Hermitian operator corresponding to measurement of a single qubit in the Hadamard basis. So now we've found what the operator must look like. And remember, again, our only requirements from lambda 1 and lambda 2 are lambda 1 and lambda 2 are real, and lambda 1 and lambda 2 should not be equal to each other. So let's review our choices, okay? For A, we had 3, 2, 2, 3. So A, we had 3, 2, 2, 3. Now the question is it possible to find lambda 1 and lambda 2 that would make O look like this? Well, let's just try it out. We would say lambda 1 plus lambda 2 over 2 is 3. Lambda 1 minus lambda 2 over 2 is 2. And then if we, this equation, lambda 1 minus lambda 2 over 2 is 2, would be the same as this one. And then the equation we get for this element, lambda 1 plus lambda 2 over 2 is 3, is the same as this. So we really only have to consider these two equations right here, which says lambda 1 plus lambda 2 is 6, and lambda 1 minus lambda 2 is 4. And if we add those two equations together, we would get 2 lambda 1 is 10, which means that lambda 1 is equal to 5, and lambda 2 is equal to 1. And notice that that choice of lambda 1 and lambda 2 will indeed make this first equation true, because 5 plus 1 is 6. It'll make this second equation true because 5 minus 1 is 4. These are both real, and they are not equal to each other. So indeed we conclude that A does represent a possible, a valid expression, a valid Hermitian operator corresponding to measurement of a single cubit in the Hadamard basis. So we would circle A. Now what about B? Well, if you look carefully, you see right away that B is not a possibility. And the way that you can see this right away without even going scrolling down and looking at our expression is to notice that B is not even a Hermitian matrix. Remember, a Hermitian matrix is equal to its own conjugate transpose, which means that if you take these two elements here, they must be complex conjugates of each other. But these two, of course, obviously are not. So it does not work. And we can see it down here as well, because in this expression, these two expressions are equal, but that's not the case up here. And therefore, B is not a possible answer. Now let's examine C, 0, 3, 3, 0. So C is 0, 3, 3, 0. Now, notice this is a Hermitian matrix because these two numbers are complex conjugates of each other. Because, of course, the complex conjugate of a real number is just the number itself. So this is Hermitian, and so it's not eliminated on the basis of being non-Hermitian, as was the matrix in B. But can this matrix be expressed in this way? Well, let's just check again, just as we did for A. We would have lambda 1 plus lambda 2 over 2 is equal to 0, and lambda 1 minus lambda 2 over 2 is equal to 3. Those are the only two independent equations that we get. So the first equation would imply that lambda 1 plus lambda 2 is equal to 0, and the second equation implies that lambda 1 minus lambda 2 is equal to 6, and if we add those together we get 2 lambda 1 is 6, or lambda 1 is equal to 3, and therefore lambda 2 would be equal to negative 3. And sure enough, if we substitute those values in, 3 plus negative 3 is indeed 0, 3 minus a negative 3 is indeed 6, and so the use of these values for lambda 1 and lambda 2 would make this matrix identical to the matrix given in C, and therefore C also works. So we would want to circle answer C. Now what about D? Well, D is a Hermitian matrix, so we can't eliminate it on the basis of being non-Hermitian. But notice that the diagonal terms here are 1 and negative 1, and when we're looking at a Hermitian operator corresponding to the Hadamard basis, we found that the diagonal elements must be equal to each other. So there's no need for us to even consider the equations and try to find lambda 1 and lambda 2, because it's clear here that for the Hadamard basis, the diagonal elements have to be the same, but in this case they are not the same, and therefore this is not a valid Hermitian operator corresponding to measurement of a single cubit in the Hadamard basis. So that's how you would do example 1. Now let's take a look at another example problem. So now let's look at example 2, which I encourage you to compare to example 4.3.4 in your text. This one says, circle each of the following that represents a valid Hermitian operator corresponding to measurement of a 2-qubit system with respect to the decomposition V equals S0 plus S1, where S0 is generated by phi plus and psi minus, and S1 is generated by phi minus and psi plus. And the choices are given here, A, B, C, and D. And I just want to recall for you here, okay, S0 is generated by phi plus and psi minus. S1 is generated by phi minus and psi plus. And remember that those vectors, those kets, phi plus, psi minus, and actually I guess I should put the ket symbol here, so let me go ahead and do that for each of these, and the same thing down here. Remember that those are defined as given here. Phi plus is 1 over the square root of 2, 0, 0 plus 1, 1. Psi minus is 1 over square root of 2, 0, 1 minus 1, 0. Phi minus is 1 over square root of 2, 0, 0 minus 1, 1. And finally, Psi plus is 1 over square root of 2, 0, 1 plus 1, 0. So if we write out the projectors for each one of these subspaces, it's just as we did before. We take the bra form of each ket in the basis. So here's the first ket in the basis for S0. We're looking at P0 first. So here's the first ket in the basis, and notice that here we've written down that ket, and then we follow it by the bra form of that same ket. And here we take this ket and follow it by the bra form of that ket. We do that for S0 to get P0, and we'll do it also for S1 to get P1. Here's the first ket and the bra form of that first ket, and then the second ket and the bra form of that second ket. So, and just for a quick review, that's exactly what we did here in the first example. Here we had just one ket in each in the basis for each subspace. So we took that ket and the bra for that ket. That was for here's a better point here. So we had that ket and the bra for that ket, this ket and the bra for that ket. So when you have just one ket in the basis, you'll get just one term in the projector. But if you have two terms in the basis, then as we see here, you will get two terms in the projector. One is obtained from the first ket and its bra, The other one is obtained from the second ket in its bra. So this is how we obtain these projectors. And then, as before, just as we did in example 1, we take the two projectors and take lambda 1 times one projector plus lambda 2 times the other one. Of course, if we have a decomposition into more than just two subspaces, then we'd have lambda 3 times the third projector plus lambda 4 times the fourth projector, and so on. And remember, our requirement is just as it was in this case. These lambdas must be real, and they must be distinct from each other. So we have the same restriction down here. We're going to have lambda 0 p0 plus lambda 1 p1, where lambda 0 and lambda 1 are real and not equal to each other. So now all that remains really is just some algebra, and I'll walk you through some of this. So let's look at what we get for P0. Okay, for P0, notice that, as was mentioned before, we have two terms here in P0, and notice that in each one of those terms, we have a 1 over square root of 2 and a 1 over square root of 2. Here's 1 over square root of 2, 1 over square root of 2. So that's a 1/2. And remember that P0 is getting multiplied by lambda 0. So I'm just going to pull that 1/2 out of both of these terms and write lambda 0 over 2 out front. And now let's see what's left. Well, here we'll get 0, 0, 0, 0. I brought that down here. 0, 0, 1, 1 right here. 1, 1, 0, 0 right there. And 1, 1, 1, 1 coming down right here. And now for the next term, 0, 1, 0, 1 coming down here. 0, 1 times a minus 1, 0. So that's minus 0, 1, 1, 0, which we have here. And then here, minus 1, 0, 0, 1. Minus 1, 0, 0, 1. And then finally, minus 1, 0 and minus 1, 0 gives plus 1, 0, 1, 0, which we have here. And in a similar fashion, for P1, P1 is getting multiplied by lambda 1, and each one of the terms in P1 also has a 1/2 factor, so I'll have lambda 1 over 2, and then the multiplication here is very similar to what we have for P0, so I'll let you do that yourselves. Now when you take a look at these two terms that we've just generated, you see that there are a lot of similarities which help us to combine all this and write it a lot more compactly. For instance, the 0, 0, 0, 0 operator is common to both, so we'll factor it out, and that's getting multiplied by lambda 0 over 2 plus lambda 1 over 2, which I can write as lambda 0 plus lambda 1 over 2. Similarly, the 0, 0, 1, 1 operator is common to both, and here it's multiplied by plus, here's plus lambda 0 over 2, and here it's multiplied by minus lambda 1 over 2. So we have lambda 0 minus lambda 1 over 2 times the 0, 0, 1, 1 operator. Similarly, here's the 1, 1, 0, 0 operator that's common to both. And here it's getting multiplied by lambda 0 over 2. Here it's getting multiplied by minus lambda 1 over 2. So we have 1, 1, 0, 0, lambda 0 minus lambda 1 over 2. And you can see that, in fact, each one of these operators is in common to both terms. And so just all that remains to be done, really, is to find out this coefficient in each case. So we come up with O, the operator, being equal to this expression right here, where we have these altogether 8 operators multiplied by certain coefficients. Now all that remains or almost all that remains, is just to get the matrix form of this. And to get the matrix form, I've lightly written these numbers under each part of each operator to help us know where those terms give us entries into the matrix. What we mean is this. The 0, 0, 0, 0 operator gives us a 1 in the 1, 1 entry of the matrix and a 0 everywhere else. The 0, 0, 1, 1 term gives us a 1 in the 1, 4 entry. And what I mean by 1, 4 entry is row 1, column 4, which is right here, row 1, column 4. The 1, 1, 0, 0 entry is 4, 1, so that's row 4, column 1, down here. 4, 4 is here, and so on. We learned in a previous lecture how to get the matrix representation for each one of these operators, and in each case it will be a 4x4 matrix with all zeros except for just one entry of 1, and these lightly written numbers indicate where that 1 appears. So again, in the 1, 1 element here, and the 1, 4, 4, 1, 4, 4, 3, 3, 3, 2, 2, 3, and in the 2, 2 element. So if we put all of that together with the correct coefficients in each case, we finally arrive at this 4x4 matrix. And let me read this off to you just to make sure you get it. We have a 0 here, and here, 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 and here. Lambda 0 plus lambda 1 over 2 in all of the diagonal terms. And then lambda 0 minus lambda 1 over 2 in the upper right-hand corner and lower left-hand corner. And then in these two terms, we have lambda 1 minus lambda 0 over 2. And again, remember that any matrix having this form, where lambda 0 and lambda 1 are both real, and lambda 0 is not equal to lambda 1, any such matrix will be a valid Hermitian operator corresponding to the measurement of a 2-qubit system with respect to this decomposition shown here. And so if you check A, B, C, and D versus that form given there, you will find that the correct answers are B and D. B is obtained by picking lambda 0 equals 1 and lambda 1 equals 3. D is obtained by picking lambda 0 equals negative 1 and lambda 1 equals 1. But choices A and C are not possible. These two are not possible. It's easy to see that A is not possible because notice that all of the diagonal terms are the same here, but that's not the case in A. So it's clear that A is not correct. And why is C not correct? Well, notice that these two corner terms, the upper right-hand corner and lower left-hand corner, are the same, but these two terms are equal to the negative of that. But here in C, all four of those terms are the same. So clearly that's not possible either. And if you check B and D, they do fit the given pattern. All the diagonal elements are the same in both of them. And for the off-diagonal terms, or for the other diagonal, we might say, the two corners are the same, and then these two are the same. So B and D is the answer to this example. So I hope that these two examples have helped to explain the examples, the main examples in this section of Chapter 4. And now we should look at some problems. So in problem 13.1, you're asked to circle each of the following that represents a valid Hermitian operator corresponding to measurement of a single qubit in this basis. Now remember, above, in our first example, we used the Hadamard basis. Here we're using another basis. And so you pick each of them, each of these matrices that represents a valid Hermitian operator corresponding to measurement of a single qubit in that basis, circle. And then for 13.2, well, this is like the second example. It says circle each of the following that represents a valid Hermitian operator corresponding to measurement of a 2-qubit system with respect to the decomposition V equals S0 direct sum with S1, where S0 is generated by 0, 0, and 1, 1, and S1 is generated by C plus and C minus. I think the answer to this one might surprise you a little bit. And I'll tell you that the algebra is not nearly as bad as you might expect. So anyway, here are your 4 choices, and again, pick all the possibilities that are correct. And then finally, 13.3 will be given in class. So that concludes lecture 13, and good luck.